Very easy problem. Okay, so let's solve this problem. But how do we begin? So basically, a good way can be to break these into the forms of each. Yeah. So basically, sin x is e to the power ix minus e to the power minus ix by 2. Yeah. And this one is by 2i. Yeah. And this one over here is e to the power x minus e to the power minus x by 2. So we'll try to break these to functions in terms of these expressions. If we do that, we get integral from 0 to infinity x square times over here we will have e to the power ix minus e to the power minus ix. Yeah, and 2 cancels out, so we have 1 by I over here. And for this, for sin as x, we basically have e to the power x minus e to the power minus x dx. Now what can be the next thing? To simplify this, we can basically take it to a geometric uh, sum, infinite geometric sum. And if you ask me how, I will share with you, don't worry. Okay, so basically how? We can basically multiply by e to the power minus x. That gives us 1 minus e to the power minus 2x dx. Now we have a geometric ratio, and since x goes from 0 to infinity, our ratio e to the power minus 2x will always be less than 1, less than or equal to 1. Okay, so 1 by I integral from 0 to infinity x square e to the power ix minus e to the power minus ix, and then this is sum going from n equals to 0 to infinity of e to the power minus ex times e to the power minus 2nx. Okay, now let's take these constants inside the sum and interchange the sum and integral. So we have sum from n equals to 0 to infinity, integral from 0 to infinity x square. Yeah, and this is basically okay. Let me do one more step, and then we will use. Okay, so this is basically e to the power minus x to n plus 1. Yeah, so we have now we can now like merge this. Yeah, so 1 by I, so I'm going from n equals to 0 to infinity, integral from 0 to infinity x square, and then this is e to the power minus x of 2n plus 1 minus I minus this is e to the power minus x of 2n plus 1 plus I. Yeah, now this is simply in the form of the complex gamma function. So basically there's no term such as complex gamma function, but I just named it. This is actually Laplace transform. So e to the power minus st x to the power n dx. In this case, the Laplace transform will be gamma of n plus 1 by s to the power n plus 1. So we'll use that thing, and so we get 1 by I. So I'm going from n equals to 0 to infinity. Over here we'll have gamma of 3 for the first one by 2n plus 1 minus I cube minus again gamma of 3 by 2n plus 1 plus I cube. Okay, now how do we find this sum? Yeah, so we have basically made some good manipulations till now, but the question is now how do we find this sum? Okay, So for that, first of all, what we can do is we can take the gamma of 3 is 2 outside, 2 by I, sum from n equals to 0 to infinity, yeah, 1 by 2n plus 1 minus I cube minus 1 by 2n plus 1 plus I cube. Now, to find the sum, we have some things known as polygamma function. So basically, first of all, we have digamma function. Yeah. So digamma function is basically defined by this recurrence relation. Digamma of 1 plus x as digamma of x uh, plus 1 by x. Yeah. And digamma of 1 is basically the Euler-Masonry constant. And similarly, we have trigamma function, which is the derivative of digamma function. So that's why we have trigamma function of 1 plus x equals trigamma function of x minus 1 by x square. Similarly, we have the derivative of trigamma function. This can be told as quad gamma function, but I'm not really sure of that thing. And then differentiate this plus 2 by x cube. Yeah. So these are the polygamma functions. And basically, now related to this sum, there are sums as well related to digamma functions, which can be changed to polygamma functions. So let's see how. This one over here is basically the well-known formula, and there are also videos on my channel which will prove this. You can check the digamma playlist. Yeah, 1 to infinity, 1 by n minus 1 by n plus x. If we differentiate this, we have digamma of 1 plus x as this goes to 0, and then sum from n equals to 1 to infinity, this is also go to 0, and we have 1 by n plus x whole square, because these are constants, so that's why they go to 0. Now, okay, now what we can do is we can basically get this from 0 to infinity. Okay, I'll make a slight modification in this sum for the sake of simplicity. Let this sum go from 0 to infinity, and let me write over here n plus 1 plus x whole square. Now we can replace x plus 1 by z. Diagram of g equals to sum going from n equals to 0 to infinity 1 by n plus g whole square. Now we can find this is trigamma, sorry. Now we can find the quad gamma function. The quad gamma function will be basically the derivative of this expression. So that minus 2 times sum from n equals to 0 to infinity 1 by n plus g whole cube. Yeah. So that's why now this was the sum that we wanted. So that is actually equals to quad gamma of g by minus 2. Now, like, what is the benefit of writing the sum in terms of quad gamma function? You might ask me that. The idea is there are some interesting properties about quad gamma function that can be helpful. Yeah. And let us find those properties, and then we will go to solution first. Then go to we will solve solution. Now basically we have digamma of 1 minus g minus digamma of g. This is pi uh, pi cot pi g. Yeah. Now if we differentiate this, we will get minus of digamma of 1 minus g minus digamma of g is equals to minus pi square cosec square pi g. That's why I have removed the minus sign. Sorry, okay, trigamma. Now again, if you differentiate this expression, you're gonna get minus quad gamma of 1 minus g plus quad gamma g. So this will be pi square 2 cosec pi g and minus cosec pi g quad pi g. That's why we can multiply both sides by negative sign. Then we will get quad gamma of 1 minus g minus quad gamma of g as or 2 pi cube, uh, and then this is basically cos pi z by sine cube pi z. Yeah, I think this is the formula. Okay, for the reflection. So basically, if once we take the sum in terms of quad gamma, we can use such properties, and this can be helpful. So that is the motivation for changing the sum to quad gamma. Now let us do that. But first, we also need to have uh, n plus z over here. But here is it's not. So that's why we will take 2 outside, and since there's a cube, it will be 1 by 8. So I'm going from n equals to 0 to infinity 1 by n plus 1 minus I by 2 cube minus 1 by n plus 1 plus I by 2 cube. Okay, so what's our next step now? This is 1 by 4i. Yeah. Now this is just, we already derived that this is quad gamma of z by minus 2. Yeah, that's why let us have 1 by minus 2, and then quad gamma of 1 minus I by 2 minus quad gamma of 1 plus I by 2. Now we can notice that we can basically use the reflection formula over here. Yeah, this is minus 1 by 8i, and then this is just 1 minus, sorry for the this thing, so 1 minus 1 plus I by 2 minus quad gamma of 1 plus I by 2. Now we had a formula for this, yeah, and that was 2 pi cube cos pi z by sine cube pi z. So we have minus 1 by 8i, and then we have 2 pi cube cos pi times our g is 1 plus I by 2 by sine cube pi times 1 plus I by 2. Yeah. Now to evaluate this, I don't think it will be a lot of trouble for us. So basically this is cos pi by 2 plus some angle, so that is just minus sign, yeah. So minus 1 by 8i into 2 pi cube. So this is just minus sign I pi by 2. Okay. So by now cos sine pi by 2 plus some angle is just cos cube. Cos cube I pi by 2. Yeah. So minus minus cancels out, and we have I over here. Okay. So we have pi cube by 4i. Yeah. Now sine of, you might have known that sine of I theta is equals to I sine s theta, and cos of I theta is equals to cos s theta. You can derive this from the complex definitions of sine and cos. Yeah, it's not that hard. I sine as pi by 2 by cos as q pi by 2. Now the I cancels out, and it had to cancel out because we had to get a real number and not an imaginary number. And this is also beauty of maths that I love. Pi cube by 4. Now this can be written as tan as pi by 2 sec h square pi by 2. Yeah. Let me check if this is the correct answer or not. pi cube by 4, 10s pi by 2, second square pi by 2. Yeah. So we solved this problem. This problem was really easy. No, no, it wasn't really that easy because we needed these sort of cool stuffs. Yeah. But with this tool, after having this tool, no doubt it's not too hard as well. But yeah, if someone doesn't have those tools of quad gamma, then how on earth will you evaluate such sums involving cube? Yeah. Okay, so basically there's also another version of Freeman zeta function as well uh, to evaluate this. But yeah, basically for a beginner, it is as equal as impossible, I should say. Okay, but yeah, we have done this problem, and one challenge is like try to solve this problem with x to the power 2n. Try to solve that if you can. Yeah, and to talk about the flow of the problem, we basically took them to the powers of e, yeah, and then used the geometric infinite sum, and then the gamma function. Oh, basically I forgot the symbol over here. And then the quad gamma function, and then reflection formula of quad gamma function, which we derived over here. Yeah, and then we got the answer. So basically, it was just e representation, gamma function, a quad gamma function, and the hyperbolic function. That was it. Hope you enjoyed the solution. Thanks for watching, and thanks to Sigma Point for suggesting this problem. This was really beautiful problem. And yeah, look forward to in the upcoming videos to keep suggesting such problems for the channel.